All right. Hello, everyone. Thanks for coming. I hope you have been enjoying the conference so far. I want to start with, you notice I put these slides on a couple of minutes early. The reason I do that is the very first time I was teaching a course in the university, like when I joined academia 6 years ago, I started the class day one, and I'm telling everybody, welcome to CS 101. And that was enough. I realized everybody is looking at each other, and then some people started prepping to leave. And I was like, these people don't know what course they are taking. But it was me who was in the wrong room. So I tried to avoid that by putting the slides so everybody knows what to expect. All right, a little bit introduction about me. So my name is Ryan Rad. A little bit close to, I would say, a little bit over to 15 years in AI. I don't want to bore you with the details. We have a full agenda, but yeah, I work in industry for a couple of years. Several years. Machine learning engineer, research scientist, software developer, team lead, and recently, like last 7-8 years, it's been mostly AI advisor. And my main advising is nowadays to a lot of companies is do not use AI. There's this company I was talking to the other day, and they were just trying to put, they were trying to find the most optimum arrangement of putting sensors. And I was like, how do we use AI? I was like, yeah, I don't think there is any way. You better not use AI, right? So this is not an AI problem because you have a concrete optimization criteria that you want to optimize and why. I mean, there's nothing you have to kind of learn here, right? So you can do a much better job, and you're much better off not using AI. So in academia, I did a lot of teaching. The last 6-7 years, it's been 45 classes across different topics. I built a bunch of different programs, a specialization. I found that a very intellectually challenging and nice task to do. And just last year, the very first master level formal generative AI course in North America. I think that's enough. So I'm from Vancouver, Canada, and my first time in Sweden. What a beautiful city, and what a nice conference, by the way. So for those of you who don't know, Vancouver is also a very nice city. And one of the coolest things about living in Vancouver is that we get to experience everything after everyone else in the whole world. So soon it's going to be New Year, right? Everybody is doing fireworks, and they say, oh, they can't believe it's 2026 already, and we can't believe either, because it's not, until 24 hours at least. All right, so I'm just wondering, how many of you were in my talk yesterday? Oh, a lot of you. That's why you're not laughing to my jokes. All right, so I'm starting from yesterday, I'm starting with LLMs to kind of set the stage for our today's topic, which is computer vision. So generally nowadays, a modern LLM kind of consumed, we think they consumed around 10 to the power of 13 tokens. That's equal to, if we encode each token with 2 bytes, that's equal to 2 to the power of 2 to 10 to the power of 13. Okay, now let's compare that with how much we can consume in terms of text. That would be interesting, right? So let's start with the reading speed of human. So a person reads, on average, 270 words per minute. That's equivalent to 4.5 words per second, or 12 bytes per second, right? Are you following so far? Okay. Now, I just want to see if you can guess, how long does it take for a human, in terms of number of weeks, months, years, to read the exact amount of text and data that an LLM is being exposed to? Would be. Sorry? That's a very good answer, actually. I have one calculation for you, and that is, if you read 12 hours per day, pretty ambitious, it would require 100,000 years to consume the same amount of text that an LLM does, right? That might sound like a very bad news because we might think of LLM as being the god and we can never reach them, right? But that's not true. And I have another calculation that I'm not putting here, and that is with the actual average reading time of human globally. Does anybody know on average how much we read every day?
Including internet?
Reading, yeah. It could be for leisure or whatever. 1 hour is, I mean, I wish it was 1 hour. I think it turns out, I looked up this morning, 16 minutes on average. So I'm not going to put that number, how long that's going to take. But here's one interesting, and I'm trying to actually show you that you're in the right session with this. Let's compare that to vision now for a second. So we have two optical nerves, and then each of them have about 1 million nerve fibers. And they can transmit about 10 bytes per second through our visual nerves. So that's how much we can consume by looking and observing the world around us. So by age 4, a child has been already awake. Usually they are asleep most of the time, right? But they have been awake roughly around 16,000 hours. That would approximately be 100 times the information an LLM can consume, a modern LLM today. So that comparison just tells you the importance of vision, and we can't get anywhere with AI if we don't get that component right. It's extremely important. All right, so I'm going to walk you through, I would say, 25 years of history in computer vision. And if that has scared you, the doors are locked, so you can't leave now. But we're going to do a super quick walk through 25 years of computer vision, where we are right now, what are some of the challenges we are facing right now, and actually what is happening in this space. So I'm going to get started by showing you a photo. So I was doing computer vision 2012, and even before that a little bit. I would say 2008, I started computer vision. So if this is a computer vision system, like let's say object detection you want to build, and your model tells you, oh, I found a horse, and you will be so excited. Wow, such a smart model, right? And but wait, it's just saying 59% confidence. That's a little bit worrying, but it's really hard to complain, right? It's getting it right, and it's over 50%, so who cares now? But the same model will, next frame in the video, this is like 100% reality. Well, I'll tell you, I found another horse. And good news, I'm way more confident than I was with the previous frame. And you're like, okay, so the way you react to this was very different. Before 2012, you would say, it is what it is, right? It happens. In 2025, you would say, oh, wait, there gotta be a bug here that I have to fix. This can't be it, right? So that's the beauty of computer vision over time. The traditional computer vision was all about like very interesting, like geometrical, computational problem, dealing with features that can stay meaningful. True transformations, right? So you want features that do not change their meaning when you rotate the angle, right? And when you change the scale, you don't want them to break, right? And there were like decades of research on that area up until 2012. And then everybody knows what happened in 2012, right? When AlexNet came out. So for those of you who don't know, ImageNet is just this extremely important, very significant challenge in computer vision and computer science. So this isn't premier event, then people would go and showcase their knowledge in computer vision, right? So this is the model that I have. It works amazing. Let me show you what a score I get on ImageNet. Usually, it was a very, very close competition. Like top solution, second top, they were like less than 1% away, like very, very small differences. In 2012, there was one winner that had a very high margin that we have never seen before. And that was around 9-10% better than all other models. And look at the difference between the second and the third best model. So that was the beginning of our CNN era, right, 2012. So between 2012 and 2020, there were lots of invention in computer vision and deep learning, I would say. And you see, like, all these different models are coming out. Each of them have an extremely important new component or new finding. And the performance was just getting better and better and better. And one thing that I want to pause a little bit here, because this is extremely important before we talk about how transformers change things, right? And that is, in CNNs, we always say they learn hierarchical representation. But how? How do they know what features they have to learn at what level? Sounds very magical, right? They do it all the time. But how? So regardless of what CNN models you're going to train with, and regardless of what data set you're going to use, they're always going to learn hierarchical feature representation. How do they do that? Well, the answer is we force them. How? By those max poolings. So technically, there's this concept of receptive field in computer vision. That is how much information a layer have access to from the previous layer. Right? And at the very beginning, they see these tiny patches of the image. There is nothing else they can do except extracting very, very low-level features, because that's all they see. And when you apply a max pooling, you're going to enlarge that receptive field by a factor of 2. So now they see an area that is twice bigger than the area they have seen previously. They have to learn features that are one level higher in the hierarchy. And we force them by those downsampling layers. And those are common in all CNN models, right? So that's the beauty of CNNs, right? You don't need to be worried about what feature is going to work for what task. And also, you don't need to be worried about how do you customize that for different data sets across different tasks. They will learn what matters for that particular data set and then for that task. So let me show you another vision of how things has changed. So before 2020, you would go to these conferences, and oh God, I missed all those days. You would see all this different variety of techniques being applied in different fields. Like, they were mind-blowing. You would get exposure to a lot of different ideas from different disciplines. So people in speech processing were doing completely different stuff. They had their own architecture. DBN was very common there. In Gen AI, everybody was doing GANs. In natural language processing, it was LSTM, RNN, right? And reinforcement learning, it was DeepQ networks, and so on and so forth. Then after 2020, wherever you go, everybody talks about transformers. It's good in a way that now a lot of people can talk to each other, right? We can understand our language, each other's language better. But in a sense, there is not much creativity going on anymore. There is not this like interesting ideas that you can steal from computer vision, apply to NLP or vice versa, and then see magical results tomorrow. I'm going to show you another version of this that I like better. That's what I call the throne swap. So before 2020, everybody was looking up to CV, and actually we owe a lot of advancement in deep learning to computer vision, because computer vision was where we learn how to do transfer learning, Bash normalization, residual net, or residual connection, and so on and so forth. We learn all of those, obviously CNNs, right? We learn all of those from computer vision, and after 2020, that's why I'm doing NLP now. Everybody's looking up at NLP thanks to transformer architecture, right? But like first of all, let's quickly look at how, if you use transformer in computer vision, what's going to change in terms of how we're going to represent our visual information. So in CNNs, we have this multiple stack of convolutional neural network. They extract feature at different hierarchical level. But the problem is, no, it's not a problem. There's a big assumption with CNNs. They work so great, but there is one big assumption, and that is the locality. In CNN, we always say, you don't have to look far. Just look at this local neighborhood. This is where you have to focus on, and don't worry about other areas. We're going to learn them in other layers, right? You don't need it now. That's a big assumption that we are doing, right? And that's why CNNs were amazing and also very easy to train. You could train them with little data. I mean, with today's standard. And so Vision Transformer will remove that assumption completely, will relax that. So when we apply transformer, we don't want to have that assumption that, oh, we can only look at certain areas of the image to make sense of it. In a sense, we want to be able to look at everywhere for everything, right? That is kind of the whole idea of the attention mechanism in transformer. But how do we do that? I'm just going to do a super quick sum up here. In traditional CV, we were manually engineering features based on our expertise, right? You need to have domain expertise to be able to do feature engineering. With CNNs, you just have to be a deep learning engineer and put the data and the architecture together. They're going to learn automatically the hierarchical representation that is needed. True local patterns, though. We always look at the local pattern, learn stuff, do max pooling. We're going to go step by step. In Vision Transformer, you want to be able to capture global dependencies in image, true attention mechanism, and look at everywhere for everything. And we're going to see how that can materialize. It's not going to be easy, but we will see what have been done so far. So I want to start with challenges. The first thing first, what is the main difference between pixels and tokens and text? Well, if we talk to each other, you tell me, how are you doing today? I can answer with one word. We can always convey our messages with 1, 2, 3 words very concisely. How much you can do with 1 pixel? You need a lot of pixel to be able to communicate a message, right? So that actually tells us about how computer vision requires more bandwidth, and we have high resolution medium compared to text. And of course, you have a lot of variation in the scale of the visual entities, and that's not what we see from text. So if you want to apply attention mechanism at the pixel level, let's see what happens. I'm going to consider a very small image of 512 by 512. And this is an RGB image, so we have 3 channels. And that's going to give us how many pixels? 786,000 tokens or pixels. Looks okay, right? But wait, if you apply attention, this is going to become a different number that I'm not going to bother reading. So that's not doable, right? We cannot do it this way. So there's this old trick in computer vision that we always apply, and that is, you might be able to guess, patch processing, right? So this is exactly what happened in 2021, 2020, 2021, and I think we are still doing it up until today. And what we do really is we just break down the image into patches. And then, should we worry about not having the order? No, that's the same problem we had with text, right? We can do positional encoding. So that's fine. And now, if you break down an image into blocks of 60 by 60, you're going to get 700 tokens. Not bad for now. So this is what happened with ViT that came out of Google in summer 2021. So this is formally the first vision transformer we have seen. The idea was pretty interesting. Technically what we discussed in the previous slide, right? So breaking down the image into patches of 60 by 60, and then applying positional encoding to those patches, flattening them, and then kind of feeding them into a normal transformer decoder or encoder, depends on the task. The result was pretty interesting. So this is the first time we got some real insight about how potentially transformer can be used in computer vision. So they showed that in summary, if you have a lot of data, you will be able to get the advantage of transformer. The reason should not be very hard to justify why, because transformers have much less inductive bias than CNNs. So you need a lot more data to learn from with them compared to CNNs. Because with CNNs, we know where to look. With vision transformer, you don't know where you can look. It's good and it's bad, right, at the same time. So if you don't have a lot of data, probably a hybrid. So hybrid architecture is very common nowadays for computer vision. If you have a few hundred thousands of images in any discipline, you can get amazing result with a hybrid architecture. But if you have a lot of data, then you can just do transformer. A couple of months later, Microsoft came out and said, you know what? Remember that 700 token? So if you apply 700 token by 700, still too much attention. And so Microsoft said, it's very hard to scale that approach, and we have to do it more efficiently. And they came up with this oversimplified architecture. And that was, you know what? We said, we don't need pixels to attend to each other, because that's too expensive. And probably we don't even need that, right? Why on earth would you need pixels to attend to each other? So we did patch processing. Then Microsoft said, we don't even need all patches to attend to each other. We can just create this grid of 2 by 2, and then in each grid cell, patches only attend to all other patches in that area. So compromises, right? So we are kind of taking away some of the amazing freedom that transformer is offering by making it faster. And if you're wondering, oh, but this way, a patch in the top right corner will never attend to a patch in the top bottom corner. What if I'm asking a question about something in that image that requires understanding of 2 areas? They said, don't worry, we will do it in 2 stages. And that's what you see. The second stage, they shift the image, and they do another gridding, because now the patches are shifted, you can get a little bit of global long-term dependencies captured, right? And they show that, actually. You can make it 10x faster, and this is called Swin transformer, right? 10x faster, and the results gonna get even a few % more accurate than before, because maybe before we were trying to learn too many things at once, and this is just easier to train. I came to the party a little bit late, but this is a paper I was working on 2 years ago, and I just said, wait, there is another way we can do it. Maybe a better compromise, and that was, I'm just borrowing that subpixel convolution idea from Twitter paper 2019, and bringing it back here and said, you know what, so same as Swin transformer, but instead of just shifting it, we can use subpixel arrangement. That's explaining the entire paper in one sentence. The exact same complexity, but you get much better long-term dependencies, and the result will be better, but you are not paying anything extra to train these models. Anyway, so now that we have a vision transformer, what we want to do is we want to see how we can build a vision language model. That would be interesting, right? So this is just this is a vision transformer, but it doesn't generate text for you. It doesn't answer question about the image for you, right? If those are the cool things we want to do, then we want to build a vision language model. How do we do that? Because so far what do we have is just an image encoder that is very powerful. It encodes visual features from any image that you provide. Okay, so what we can do, I'm just looking at the time here. I feel really bad for being the only thing standing between you and lunch. So just want to make sure we stay on track. So we have a bunch of technical challenges with VLMs that are a little bit similar to what we already discussed, but on a different level. So one of them is LLMs are already heavy, expensive to train. We have lots of tokens to learn from. And if you add visual token, it's going to get slower, heavier, more expensive to train. So how do we do that? And the other thing is we have two completely different modalities that we want to learn at the same time. And that's a different challenge. So how do we do all of this? So I'm going to bring an oversimplified version of GPT. So this is GPT, right? Oversimplified. We only have the embedding layer. You have your input text, your embedding layer, and then it will go through the decoder and will generate the next token, right? In order to build a VLM, we need a few different components. All right, I'm just going to get rid of that and stay with this. So we need a few more components. Number one, let me bring the visual content. So this is your visual input that's coming in. And how do we understand this image? How do we know what's in there? So luckily, we already talked about that. We need a vision transformer model that will encode visual information, right? So that's the first component we need. The second thing is an interesting one. We need a multimodal projector. And I can explain this in the next slide much better. You don't want to just learn features. You want to learn features the same way. You want to learn features that are aligned with textual feature across different modalities. In this case, it's images versus text. And then finally, you need a fusion strategy. We usually just use cross-attention for this particular part. But I want to explain multimodal projector. That's the most important part that we haven't covered so far. We talked about image encoder, fusion strategy, just cross-attention. So let's talk about multimodal projector for a second. But first, I want to talk about the need for it. So this is what is called joint embedding a space. So let's say you have text, you have image or video, and you have these different pieces of text, different images or different video files. You want to find an embedding that when you perform that, an image of a dog will have the exact same embedding vector, or very similar, to the embedding vector we get from embedding the word dog. And how do we get that right now? So this is where things get interesting. I think over the last couple of years, we had a couple of different methods that people applied to get this. I'm going to walk you through that one by one. So this is the first method, which is called contrastive. And what we do is you have an image, you apply like any vision transformer to get the features. And then you have a text encoder. And then, so technically you have pairs of images and caption of those images. So you also know the description of that image. And then you use a vision transformer to encode the image, and you do a text encoder to encode the text. And you want to make sure that the embedding vectors of items that are related are as close to each other, and then they are as far as possible from other pairs. That's one way of doing it, by contrasting them as much as possible. to make sure that things that are similar stay similar, and things that are not stay far. There is another interesting approach by masking, a little bit more complicated to train, but a bunch of labs try this approach as well. This is quite interesting. You mask, so you have the description of the image, you mask part of the image, and you try to reconstruct the image so that the same caption still holds. So that's a very interesting alternative approach to this. And there is the generative approach as well. So you have, we start with a prompt, which is the description of the image. We try to generate that image, right? And then we use the same image. We apply image captioning, hoping that we're going to get the same caption, or a caption that is similar to the original one, right? So you see these techniques are just kind of evolving over the time, and these are very recent research. The whole idea is how do we align textual features with visual features, right? So this is, so one of the work, you probably heard of this one, very popular, is called Clip by OpenAI, that actually does, actually implements that first scheme that we talked about. So the way it works technically, this is what you want to do, right? So if you look at the diagonal part of this matrix, this is representing captions that belong to the images. So you want the scores, you want the similarity along this diagonal line be as high as possible. And then for the rest, it should be as low as possible, because you want to those are the wrong captions, right? So if you train a model like this, then it learns to encode images in a way that the embedding vectors are aligned, fully aligned, with the embedding that we get from text. Now, if you talk about dog, and if you show a photo of a dog, your decoder knows that you're talking about the same thing, right? So they got to be able to speak the same language, otherwise it's impossible to decode anything. So the things that we discussed, the combination of those techniques actually gave birth to a lot of VLMs. One of the popular ones out there is Lava. They use Clip, the technique that we just described. They use Vision Transformer that we also covered. And for the decoder part, they use a fine-tuned version of Llama, which is Konya, which is also open source. And they show that actually their model can outperform a lot of closed source model. And that was in itself a pretty interesting finding. And this is the last part of the talk. And we're going to talk about limitation and opportunities. So there are a lot of different CV problems that are much easier now with today's standard that they weren't before. And I also have the zigzag kind of complexity icon for you there. So you can see we solve image classification, object detection, image segmentation, video understanding. And then when Vision Transformer came on board, we were able to do more difficult tasks in computer vision, such as image captioning. We have VLMs less than 1 billion parameters right now that do an amazing job in visual QA, right? And finally, image generation, right? So this is also an area that we are seeing amazing, I would say, progress. Obviously, Nano Banana is one of the, I think, best models out there right now. But there are areas, so this is an active area of research. There are only a handful of papers, and they all came out a couple of months ago, and people figure out, if you really want to understand how VLM works and what is their limit, you need to test them on game scene understanding. So this is the new area that people are exploring right now as we speak. Very, very new. There are only 3 papers that I'm going to show you later, but they show that the state-of-the-art VLMs fail miserably to understand and make sense of the dynamics in 2D games. And that is telling us a lot. So I'm doing active research right now on building a taxonomy of failure cases when VLMs apply to game understanding. So technically, if they fail to follow the rule of the game, why is that? Is that because the perception failed? Is that because the temporal reasoning component not doing the job? Or so on and so forth. Okay, so these are the 3 papers that I said. If you're interested, I highly recommend. They all came out like 2 months, 3 months ago. So I'm going to fast track a little bit. I'm going to show you a few other things to see the limitation of VLMs in practice. You might be familiar with this. And I created so the orange circles are exactly the same size, right? I created a different version of this, which they are not anymore. And when you fit this to an LLM, to a multimodal VLM, a state-of-the-art, it actually tells you that those are exactly the same size. So why this is happening, let me show you another example, and then I'm going to quickly share an insight why this might be happening. Here is another illusion. I mean, those of you who have been in my talk, you know this one. And I created another, so these are exactly in parallel, right? I created another version of this. And it says they are parallel. So these are models that if you give them an image, they describe it with all the details, and they are failing to understand what is happening here. So the reason for that is, I mean, my take. So what I think is happening is the text portion of VLM is dominating the vision component. So the vision component is live. It's looking at the real data. The text component is looking at lots of outdated information about this particular illusion. And they think anybody who talks about this illusion is looking at the same image, right? So they kind of blinded by that fact. And that is what I call the text token dominance. This is also another thing I wanted to talk about. This paper came out last week. I think there is huge implication in this paper. It's 22 pages. I'm summarizing it in one sentence. So technically what you're talking about is it's a lot more efficient. This is mind-blowing. I think this paper got everybody thinking. What they're saying is the best way to understand text data is by taking a photo of the text. That's so counterintuitive. And I can show you some of the results, but also quickly what is happening. We are running out of time, so I have to be super quick here. So it turns out if you have a long PDF document, you need, let's say you have 10,000 of words, you probably need 15K or 20K of tokens, right? What else you can do, take a screenshot of that entire page, and you can apply, I mean, you can do that in different resolution that you wish. And then if you do low resolution, you get less visual tokens. And that's a way to summarize the information. This is such a powerful concept because you can retrieve the exact same text. And so what they're saying is, here is the result. I'm going to quickly show you that. So in the bottom, you're looking at the number of text tokens. And then they are summarizing that many text tokens with 64. The magenta color is showing 64 visual tokens only. And they're losing only 3% accuracy. So somewhere between 7 to 20x compression of long context if we process the text with visual tokens. All right. I'm going to skip this. I just wanted to say quickly that I think there's huge opportunity here that we are not capitalizing computer vision. Satellite imagery are free. We have tons of them, and we can do a lot of amazing stuff that will benefit humanity with the technology we have right now, but everybody is so busy with having fun with LLMs and multi-agent systems. Yeah, I will skip this slide. I wanted to talk. Okay, I will just Thank you. Just 1 minute, then I will spend that here. So some of the applications, right? So wildfire, let me talk about wildfire, which has been a huge problem in North America recently, last couple of years. So if you look at this chart, there are 3 ways we can tackle wildfire, right? One is detecting active wildfire, very easy to do. And when you detect it, it's too late already. So what do you do now? Prediction, you can predict when wildfire is going to happen. A more useful solution. However, you cannot predict wildfires that are human caused. They're very difficult to predict. And interestingly enough, in 2023, about 75% of all wildfire in the whole world was human caused. And that leaves us with one solution, and that is strategic spread modeling. So for active wildfire, can we look at all the data we could possibly get from satellite and model how it's going to spread over the next 6 hours, 4 hours, 12 hours? And if we can do that, we can put our resources strategically to the area that is needed the most. Thank you very much for being here today.